Okay, so we're on page 25 today, and we are gonna, again, begin to look at that process of sort of swapping between standard form of a polynomial, which we've talked about, and then this kind of grouped version of a polynomial, which is what we'll call factored form moving forward. So I'm going to start off by graphing this first function that I have, this first polynomial. So on my calculator, I'm going to add a graph page, and I'm just going to graph this function. So I have 2x cubed plus 7x squared plus 4x plus 14. That all looks good, so I'm going to go ahead and hit enter. And I have just a portion of my polynomial that's shown up here. One thing I want to point out to you guys is an issue that I frequently have is you will graph something, you will get something that looks just like a line, or you get nothing at all, and then you panic and say, Miss Lucia, my calculator's broken. Your calculator is not broken. I want you to remember that when you graph something on your calculator, you're getting a very small picture of that graph. So we're only getting this portion of our graph right around the origin. The nice thing is I can see an x-intercept here, and it's asking me for the x-intercept. So I'm going to go ahead and find that really quickly. But then I'm going to adjust my view of the graph so I can see, at the very least, my y-intercept, okay? Because I can't see that on my graph right now. So I'm going to hit menu, and then I'm going to go down to analyze graph. And an x-intercept on your calculator is referred to as a 0. So I'm going to go ahead and select that option. And then I'm just going to click with my blinky line on either side of that x-intercept. So I see I have an x-intercept at negative 3.5. So I'm going to jot that down in my notes. X equals negative 3.5. And then I'm going to adjust the view on my graph. So I'm going to go to menu, down to that window zoom option, and you have zoom in and zoom out. I personally am usually a fan of zoom fit, so I'll see what that looks like here. I do zoom fit, I get this sort of big picture view of my polynomial. That's nice if I have a kind of awkwardly shaped polynomial so I can see what everything looks like. The not nice thing here is that my scale is adjusted so much that it's difficult to see my y-intercept. So for this particular function, I'm going to go back to menu and adjust my zoom back to standard. That takes me back to my normal graph window. And then from here, I'll do menu, zoom out. We'll just zoom out. And I know I want to see sort of this. Oh, there we go. There's a good picture. I know I want to see what's going on kind of up here by where my y-intercept is. And if I just click and drag this a little bit, I can see, let me move this function out of the way. I can see a little bit better idea of what's going on here. I can see that I've got sort of a maximum here, and then we dip down to a minimum here. And I know somewhere in here is my y-intercept. It's a little difficult to tell exactly where it is from the view that I have right now. So I'm going to bring up my table by hitting the blue control button and then T on the keypad. And it brings up the table of values that match this function. I know the y-intercept happens when x is 0, so I'm going to scroll up in my table until I see where x is 0, and that would give me my y-intercept. So I know my y-intercept is 14, again, from my table and my calculator, and there's a ton of different ways you can find your y-intercept, but that table is a pretty quick option. My y-intercept is 14. And then the next question here is, which of these can be seen from standard form? My x-intercept is negative 3.5. I don't see anything even remotely close to negative 3.5 in here, but I do see that 14 at the end here. This is the same idea as when you had y equals mx plus b in algebra 1, and that guy at the end was your y-intercept. Same idea here. When I have standard form, this constant term at the end is my y-intercept. Now let's take a look at this second function. Now we've got factored form, so I'm going to go ahead and graph this. I need to start by putting away my table. So Control T will put that table back away. And then I'm going to hit the delete button 3 times really fast to get that graph out of there. It says, do I want to delete this? I'm going to say yes, hit enter. And then to graph again, I want to hit the tab key to bring up my function line. is very disappointing to type in a whole function and then nothing's happened because you didn't have the equation line up there. So make sure that you check for that before you start typing. And then I'm just going to type this function as it appears. So parentheses, x minus 2, close parentheses, open a new one for x plus 2, and then x plus 3. That looks just like my paper, so I'm going to go ahead and hit enter. And again, this graph is sort of adjusted for that last function, so I'm going to go ahead and click and drag so I can see a little bit better picture here. And I'm going to even drag this up a little bit so I can get a feel for where that y-intercept is. I can see I have 3 x-intercepts. From my graph, it looks like I can see them pretty clearly, but the nice thing about having your calculator is that you don't ever actually have to guess or estimate that that looks like where the y-intercept is. So I'm going to go ahead and hit menu, go down to analyze graph, and use that zero finder feature. So again, with that zero finder, I'm going to click on either side. Now the bummer is that you can only get one x-intercept at a time. So no matter how far I drag this, it's only going to give me one of them. It just changes which one I find. So that first one would be, it's hard to see. Remember, you can always click and drag your text around. The first one is -3. Menu, analyze graph. 0. Let me find that second one. So I want to go in between here and then cross. And I get another x-intercept at -2. And then our final one, menu, analyze, 0 is at 2, +2. Our y-intercept for this graph, I'm going to find using my table again. So Control T to bring up that table, and then scroll up. When x is 0, y is -12. So my y-intercept is -12. And then again, my question is asking me which of these can be seen from factored form. Well, we saw a problem like this already, right? Back when we talked about x-intercepts for the first time, we had our function, we had our graph with our x-intercepts, and we said there was a relationship between what I saw in parentheses for my function and where I saw my x-intercepts in my graph. So these x-intercepts, I can see from this what we're going to call factored form. They're opposite signs. So I have x plus 3, and our x-intercept is -3, plus 2, -2, x minus 2, and a +2. They're opposite signs, but I can still see them from here. Okay. So what we want is a way to be able to get any key information about our graph from the function. I know if I have standard form, I can see that y-intercept. If I have this factored form, I can see those x-intercepts. But I would still like to be able to know the y-intercept from my function. From this function up here, I would still like to be able to get this x-intercept. In order to do that, I need a way to sort of convert between these different forms. So what we're going to look at for today together in class is how to get from factored form to standard form. And then your homework, and what we're going to work on in class the next few days, will be how to get from standard form to factored form. We'll look at a bunch of different strategies for that. Okay? But again, for today, we're just going to focus on how to get from factored form to standard form. So if I have factored form of a polynomial, how can I change it to standard form? Well, I want you to remember back from our very first couple of lessons, one of the first things we looked at were those polynomial operations. So if I have one polynomial and I'm adding it to another, or I'm doing some subtraction, or I'm doing multiplication, which is what I see here. So what are we going to do to change between these two different versions of our polynomial? Well, we're simply going to multiply the factors and combine like terms. That's it. Okay, we're just going to multiply here. So this is back to what we did at the very beginning. So for this first problem that I have here, I've got 3 pieces to multiply, Right? This is the one that we just looked at where the x-intercepts are. I've got 3 pieces to multiply together. Remember when I'm multiplying, I just multiply 2 things at a time. So if you had, for example, 2 times 3 times 4, you would multiply 2 and 3, and then take that product and multiply by 4. Okay, we multiply 2 things at a time. So I'm going to start by multiplying 2 factors at a time. Whatever I get, I'll multiply by that third factor. So I'm going to start by just multiplying these first 2 pieces. It doesn't matter which 2 you multiply together to start. Just pick 2 and multiply them together. I'm just going to work through in order of the problem. So I'm going to multiply these 2 together to start. So x times x would give me x squared. And then x times a positive 2 would give me plus 2x. And then I've exhausted all of the pieces here, so I'm going to come back and multiply that negative 2. Negative 2 times x would give me negative 2x. And then negative 2 times positive 2 would give me a negative 4. Now I'm going to go ahead and combine like terms here to sort of tidy up before I do my next round of multiplication. Otherwise, you got a lot of things to have to distribute. So if I combine my like terms here, this is my only x squared term. Then I've got plus 2x minus 2x. So these are like terms I can combine. When I take 2x and subtract 2x, I have 0x. And then I've got minus 4. So I'm going to take that and multiply by my last factor here. And now we'll distribute again. So x squared times x would give me x cubed. And then x squared times 3 would give me plus 3x squared. Negative 4 times x would give me minus 4x. And negative 4 times positive 3 would give me negative 12. So this would be my function f of x equals, squeeze that in there, f of x equals x cubed plus 3x squared minus 4x minus 12. Okay. I don't have any like terms to combine here, so this is my simplified standard form for this function. And then my directions say state the y-intercept. My y-intercept here would be this constant term at the end, negative 12. Okay. So I've just changed this function from factored form to standard form so I could identify the y-intercept. Okay. And remember, this was the same problem that we graphed on our calculator. So we knew the x-intercepts and we knew the y-intercept. The y-intercept I found here from standard form matches what I found on my calculator. Okay. If they didn't match, I would have a problem. Let's take a look at one more together. Again, we're just multiplying, just distributing. So I've got 1, 2, 3, 4 pieces to have to distribute this time. I'm going to start the same way. So I'm just going to multiply these first 2 and then multiply it by the third thing and then multiply it by the last thing. You can multiply any 2 things together at a time that you want. That's fine. So your work may look a little different than mine, but I'm multiplying at the end all of these things together. I'm going to start by distributing this negative 2. That would be negative 2x minus 6. No like terms to combine there, so I'm just going to throw that in parentheses and multiply by my next piece, which would be x minus 3. So distribute again, negative 2x times x would be negative 2x squared. Negative 2x times 3 would be positive 6x. And now negative 6 times x would be negative 6x. And then negative 6 times negative 3 would be positive 18. I've got like terms I can combine here, so I'm going to clean this up a little bit before I continue multiplying. So I've got negative 2x squared plus 6x minus 6x means I've got 0 x's plus 18. And then I'm going to throw this in parentheses so I can multiply by this last term here. We've got x squared plus 5. And we'll distribute just like we did before. So negative 2x squared times x squared would be negative 2x to the 4th. Remember, as we're multiplying, we add those exponents. And then negative 2x squared times 5 would be negative 10x squared. And then I've got 18 times x squared, so that's plus 18x squared. And 18 times 5 would be 90. So plus 90 there at the end. I have some like terms to combine here. So this would give me, for my function, negative 2x to the 4th plus 8x squared plus 90. Here would be my y-intercept. So my y-intercept for this function is 90. So this is work that we've already done. We've already talked about multiplying polynomials, distribution. We've already seen that. And if you're somebody who prefers box method, you can use box method on all of these the same as I use distribution. So that's fine too. So this is kind of the old stuff. What we're going to look at now, what we're going to sort of dip our toe into now, is how do I take a standard form polynomial and change it to factored form? Okay, how do I go from this back to this, or from this back to this? How do I reverse that process? Reversing that process is something called factoring. So that's what we're going to start to take a look at next. I have a sort of practice set of a bunch of different factoring problems here in front of me. This is posted for you as well on Google Classroom. It's called Factoring Fun, I think, with today's date and tomorrow's date. You can pull this up to take a look as I'm looking at these problems or not. You're not going to have to print it or submit it to me. They're just sort of extra problems that are going to be available for you as we really get into factoring. But as we talk about factoring, one thing that we're going to look at to determine what strategy to use is how many terms each of our problems have. So that's what I'm going to go through and take a look at right now. So just if you want on some scratch paper, maybe down here towards the bottom of page 25, if you want to make a note to yourself, number 1 has 2 terms, number whatever has 3 terms. But we're just going to sort these by their number of terms, okay? So I'm going to, I think, color code mine just because that's easiest for me since I have different color markers. If you want to do circles around the 2-term problems or boxes around the 3-term problems or stars or whatever, but we just want to sort by how many terms each of these have. So you guys can see 1 through 10 right now. I want you to make a little note to yourself, however you'd like, in your packet or on some scratch paper, on how many terms each of these problems has. So take a minute to try that right now. So I can see that number 1 and number 3, and number 8 and number 9 all have 2 terms. If I scoop my paper up a little bit, there's a few more problems here that you guys couldn't see. Number 11 also has 2 terms. Number 15 also has 2 terms. Number 4 has 2 terms. Everything else on this page has more than 2 terms. So next I'm going to look at those 3-term problems. Number 2, number 4, number 6 all have 3 terms. If I scoop my paper up, I see a couple more 3-term problems here. Number 12, number 13, and number 16 all have 3 terms, right? And by terms, I mean how many distinct pieces do I have? Distinct things with X or with a constant term, okay? So 1, 2, 3 here. If I look at number 15, just 2 pieces there. The remaining problems that I see on here all have 4 terms. So 1, 2, 3, 4. So 5, 7, and 10 are all problems with 4 terms. I want to look at the number of terms that I see for a polynomial when deciding to factor, because that number of terms determines the strategy that I'll use when I'm factoring. So that's something that you're going to look at in that homework video for tonight. We'll approach 4-term problems a little bit differently than we approach 3-term problems. Those are the 2 that you're going to focus on for tonight. And then a little bit later, we're going to look at those 2-term problems, how we handle something that just has 2 terms. The last thing I'm going to look at with you guys for today is how I handle something with any number of terms that has a greatest common factor, okay? So greatest common factor, or a GCF, means that there is some factor common, right? Greatest common factor, some factor that's common to every single term in my polynomial. Another way to say that would be that I can evenly divide every single term of my polynomial by the same number, okay, or by the same variable. So if we take a look at our problems right here, let's take a look at number 3. We had, it's difficult to see, we have 54x cubed plus 2. 54 and 2 are both even numbers. That means that I can actually divide each of these terms by 2 with no remainder. 2 is a common factor to both this first and the second term. It's actually the largest thing I can evenly divide each of these by. So that's why I would call it the greatest common factor. Common factor because it's a factor of both of those numbers, right? I can evenly divide both of those terms by that number. And greatest because there's not a bigger number. I can't evenly divide both of these by 4 or by 2x. 2 is it. So what I'm going to do is factor out 2 from each of these, or divide out 2 from each of these terms. 54x cubed divided by 2. 54 divided by 2 would give me 27. So I would have 27x cubed plus 2 divided by 2 is 1. Okay. So what I've just done here is initiate that factoring process by factoring out a greatest common factor. I said if I divide everything in this problem by 2, what's left over? That's the big idea behind factoring. So we're going to do this for whatever other problems on our set here have GCFs. No GCF here. 25 and 9 don't have any common factors. And this is the only guy that has X. Number 2, no common factors for all of those terms. Technically, any problem has any 2 terms have a common factor of 1, but we're looking for stuff that's a little more interesting than that. Nothing for number 4, nothing for number 6, nothing for number 5. 3 of these have an X as a common factor, but I need all of them for it to be the greatest common factor for all those terms. Same thing with number 7. I don't have anything that's common to all my terms. Just 2 or 3 isn't enough. It has to be all of them. Number 8, 8x cubed minus 27, no GCF there. Number 9, nothing interesting. Number 10, again, nothing exciting there. I can divide some of the terms by 3. I can divide some of the terms by x, but if it's not all of them, then it's not a GCF. I take a look at these bottom problems. Number 11, I've got a GCF here, a greatest common factor. Notice that both of these terms have an X. That means X is evenly, can evenly divide each of these terms. And then 6 and 15 have a common factor of 3. They're both divisible by 3. So this 3x would be my GCF for this problem. So I'm going to factor it out or divide it out of each of these terms. So I wrote my GCF, and now in parentheses, I'm going to write what's left over if I divide that out of each of those terms. Where you have kind of multiple pieces to your GCF, sometimes it's easier to break it into parts a little bit. So I'm going to factor out that number from the other number first. So 6 divided by 3 would give me 2. And then x squared divided by x would leave me with x. And now for my next term, I have a positive 15 that I'm dividing by a positive 3. 15 divided by 3 would be 5. And then x divided by x would be the same thing as 2 divided by 2, or 7 divided by 7, or 135 divided by 135. X divided by x is 1, just like all of these others would simplify to 1. So I would technically have 5 times 1 there at the end, but that's just 5. So this would be problem 11 with that GCF factored out. As we're factoring, one important thing I want you to remember is that I can always check my work by distributing back. So if I distribute back, I would have 3x times 2x, that's 6x squared. And then 3x times 5 would give me 15x. I should always be able to distribute and get back my original problem. Okay, so I can always check my work with factoring. So this would be our factored form for number 11 with that GCF pulled out. No common factor for number 12. No common factor for number 13. Number 14, though, both of these terms have x, and the coefficients would both be divisible by 2. So my GCF would be 2x. So now I'm going to write what's left over if I divide that out or factor that out of each term. 2 divided by 2 would be 1, and then x cubed divided by x. You said a minute ago that when we are multiplying variables, we add their exponents. We had x squared times x squared, that gave me x to the 4th. When I'm dividing variables, remember we subtract their exponents. So I would have x cubed divided by x. Exponent here would be 1. So 3 minus 1 would be 2. So I would have x squared when I take x cubed and factor out an x. And then minus 32 divided by 2 gives me 16. And x divided by x, just like we talked about over here, would just be 1. So multiplying by 1 isn't going to change that 16, so I will leave that as 2x times x squared minus 16. You could also write this as 2x without the exponent, and then x squared without that 1 coefficient. Remember, those 1s are implied. And then if I take a look at 15 and 16, I do have GCFs here. I've got x's as part of each term. 48 and 4 are both divisible by 4. So I could factor out a 4. And something to do with x, I can actually factor out whatever the smallest exponent is on x. So here, my smallest exponent was a 1, so I took out an x to the 1st. Same idea here, my smallest exponent was a 1, so I took out an x to the 1st. For number 15, my smallest exponent is a 3. So I can actually take out an x cubed here. And then again, in parentheses, I'm going to write what's left over when I divide this out of each term, or factor it out of each term. 48 divided by 4 would give me 12. X to the 4th divided by x cubed would give me x. Then minus, we'll take this one as the whole term. Since I'm taking a thing and dividing it by itself, 4x cubed divided by 4x cubed would just be 1. Again, if I were to distribute back, I would get this original problem. And then for number 16, our last problem here, looks like I've got something divisible by 12 at the front of each of these. I want to take out the greatest common factor. Remember, that's why it's called the GCF. So I could divide each of these just by 2, but then I would have 6, 6, and 12. So all of those would still have a GCF of 2, or a GCF of 3. Or if I looked at the greatest common factor, I could still divide all of them by 6. The point is I could still divide all of them by something if I only factored out a 2. So I'm going to pick the biggest number I possibly can when I'm pulling out a GCF. In this case, that's going to be 12. So I can divide all of those terms by 12 with no remainder. So that would give me x to the 4th, or 1x to the 4th, plus x squared, or 1x squared. Remember, 12 divided by 12 would just be 1. minus 24 divided by 12 would give me 2. And there I pulled out my GCF for each of these sort of sample problems that I've given you. Now, what you'll look at with your homework tonight is how you can further factor something that has 3 terms, or how you could approach something that has 4 terms. Your first step is still going to be to start by pulling out that GCF. That's how we'll start every factoring problem. But once I've pulled out a GCF, there's actually still more stuff I can do with this. So that's what you'll look at with your homework tonight. Okay, I am going to stop recording at this point.